On Friday, we defined a field as a line of influence that surrounds something. Specifically, when we're talking about an electric field, it would be a line of influence that surrounds an electric charge. We defined it in another way as well. We wrote it in by hand. Do you guys remember what that second way of defining it was? Yeah? Yeah, the region in which an electric force could be experienced by an electric charge. Now, if we're talking about a gravitational field, it would be a region in which a gravitational force could be experienced by an object with mass. Okay, electric field, a region in which an electric force could be experienced by an object with charge. We know that electric fields surround electric charges, just like gravitational fields surround objects with mass. And we know that electric fields and gravity fields, for that matter, are both vector fields, meaning that they both have a direction associated with them. Unlike something like a light field or a heat field, light travels in a particular direction. If I turn on a flashlight right here, it's going to travel from me to you, but that doesn't mean the influence of light is in a particular direction. Okay, the velocity is a vector, but the influence is a scalar. Hence, we'd say that vector fields, gravity, and electric fields, scalar fields would be things like light and heat. Now, we distinguish between a field and a force as well. We said a field is that influence that's there no matter what. As long as we have something to cause it, it's going to be there. Let's think back to gravity again for a second, because it's easier for us to visualize since we experience it every day. We feel it, literally feel it every day. The gravitational field surrounding the Earth is about 9.81 meters per second squared. Depends upon where you are. It can be a little bit bigger than that or a little bit smaller, but on average, it's about 9.81. Now, that field is there whether or not we have somebody or something to experience the field. So let's say right there, with the point in space that I'm pointing at right now, gravity is 9.81 meters per second squared. If I was to all of a sudden put my water bottle at that spot, then it's still 9.81 meters per second squared there. The Earth is producing the field whether or not the water bottle is there to experience it. The field is there as long as there's a producer there. But if we put the water bottle there, there's not only a field, but there's also a force. Because now we got something not only to produce it, but we now have something to experience it. The Earth produces it, the water bottle experiences it. In order to have a field, you got to have something to cause it. In order to have a force, you got to have something to cause the field, but also something to experience the field, like the water bottle. If we make the transition from gravitational fields to electric fields, well, it would be not the Earth that's causing it, it would be a big charge. The experiencer would be another charge, typically a smaller charge. Okay, the field is there, whether there's anything there to experience it or not, but the force depends upon that second smaller charge being there to experience it. Finally, we define the direction of the electric field in two ways. Number one, we arbitrarily define it as the way that a positive charge would move if placed in the field. Here's a positive producer right here. There's field lines surrounding it. Which way do they go? Don't know. Well, let's put a positive experiencer in there. Which way is that positive charge going to go as a result of that other big positive charge? It's going to go away from it, right? It's going to go away from it because it's repelled by this positive charge. That means that the field surrounding this is going to be away from the positive. Now, what if I took this away? Does that affect the field? No, it doesn't affect the field any more than if I take this water bottle away from the Earth's gravitational field. The field is 9.81 experienced by this water bottle. If I take the water bottle away, what's the field at that point now? 9.81, even if there's nothing there to experience it. We just say the field direction is the way that a positive particle would move if it was placed in the field. It may be there, it may not be there, but if it was there, which way would it go? Let's take a look at if we had a negative producer. If we put a positive charge right here, where would it go? It's going to be attracted towards it, right? So it's going to go this way, right? Toward the negative producer, attracted towards it. That means the field points inward toward the negative producer. Now, if we took this away, it's just like taking the water bottle away, the field still is there, and it still points in the same direction. We say it's the way that a positive particle would move if it was placed in the field. Basically, positives go with the field, negatives go against the field. So we define it in those two ways, the way the positive particle would move if placed in the field and away from the positive and toward the negative. We're going to draw a couple pictures here. We do these on Friday, but we'll draw them again here just as a review, and then we'll get into some new stuff here. Let's say we've got a positive producer right here and a negative over here, and let's say that they're independent of each other, so they're not close enough to affect each other. Just did this, right? Field surrounding this one would be this way. Surrounding this one would be this way. Toward the negative, away from the positive. What if I put them close enough together though to interact? So let's say we had a negative right here and a positive right here. Field lines toward the negative. Field lines away from the positive. These field lines join together like this. We know these two charges will attract each other because they're opposite charges, but we also know they'll attract each other because the field lines join together. When they join together, that means they're going to attract each other. But what if I have this? What if I have two negatives close enough to each other to interact? Field lines don't join together, they repel each other. When the field lines don't join, that means they're going to not attract, but repel. We know that anyways, really, because negative and negative repel each other, right? Sometimes you may see diagrams that look a little bit different than this, though. Maybe the configuration is a little bit different. Maybe there's 3 charges in there. Maybe the shape of the charges is a little bit different. Okay, what I want you to remember is that if the field lines join together, we know they attract each other. If they don't join together, we know they repel each other. Sometimes it may be, in these cases, right, it's easy to see when they attract or repel. Sometimes it may not be so easy to tell. Join together, they attract. Don't join together, they repel each other. Okay, regardless of what the diagrams look like. All right, let's take a look at some math here. What you see up on the board right now is just a review of Physics 20. This first equation, actually, we did talk about it briefly earlier on in this unit when we were talking about the electric force equation, Coulomb's law. Let's go back to gravity again for a second. Back to Physics 20. This first equation describes for us the force that exists between 2 objects with mass. If you get the Earth and the Sun, the force of gravity between the Earth and the Sun would be found by this equation. If you have 2 people, the force of gravity, a ridiculously small force of gravity, would be found by this equation. This equation finds for us the force of gravity. There is a similar equation that we've done this year that finds for us the electric force, and it looks almost the same. It's what we call an inverse square equation. They both are. Instead of gm1 m2 over r squared, it's kq1 q2 over r squared. Same structure. Difference, well, electric force is bigger. Electric force can be attractive or repulsive. Gravity's got to be attractive, but lots of similarities for sure. You guys might recognize this next equation here? You got to think way back for that one, because that's definitely Physics 21. We haven't addressed that this year yet. This is the strength of the field, the gravitational field. When we know information about what caused the field, we call it the producer equation. If we know something about what caused the field, we would use this equation. If we're talking about the water bottle and the Earth, The Earth would be producer, the water bottle would be the experiencer. If we knew something about the Earth, then we would use the producer equation. Similarly, if we have two charges, one's causing, one's feeling the field, what would be the producer equation? Take a stab at this. I think you can get it. I'll give you the symbol for electric field. Symbol for electric field is E with the arrow over it. And we usually put F over it. Yeah, good. KQ over R squared. If we know something about what causes the field, then we would use this equation. Q being, by the way, the charge of the producer. Because you will have a charge of the experiencer as well. You don't use it. The charge of the producer. Finally, this would be the field experienced by something. Gravitational field experienced. If we wanted to find the electric field experienced, we would say E is equal to F over Q. Q being this time not the charge of the producer, but the charge of the experiencer. In coulombs. So basically it boils down to this. You want to find an electric field, decide whether you know more about what causes the field or what feels the field, what experiences the field. And then use the appropriate equation. Here's a rule of thumb. If the field exists at the point where the charge is, listen carefully to what I'm saying here, okay? If the field exists where the charge is, then you've got an experiencer. So in other words, if I said, oh look, here, right here, the field strength is 10. Here's a negative charge. That's experiencing that charge. If, on the other hand, I said, oh look, the field over here is 10. Here's a negative charge. Well, then that must have been producing the field over here. Make sense? If you're where the field is, you're an experiencer. If you're a certain distance away from the field, you've got to be a producer. Sometimes it's a little bit tough to tell whether it is a producer or experiencer. If you're where the field is, you're an experiencer. If you're away from where the field is, you're causing it. Okay, it's kind of like, well, you said the gravitational field strength right there is 9.81. Water bottle is right there. Does the water bottle produce it or experience it? Experiences it because it's where the field is. Does the Earth produce it or experience it? It produces it because the Earth is a certain distance away from where the field is. Yeah, Matt? Yeah, R is the distance between the center of the producer and where the field is. Yeah, so general rule of thumb, look, if you got a value for R, generally you're going to use the producer equation, usually. Yep. So let's take a look at a problem here. There's three problems that we want to do today. This is the first of the three. So it says a sphere with a negative charge of 2.1 times 10 to the negative 6 experiences a force when it's placed in the electric field produced by a source charge. It's the magnitude of the electric field that the source charge produces at the sphere. You know what? Let me draw this out, okay? Don't take shortcuts. If it's useful to draw a picture, then draw a picture. If it takes you 10 seconds to draw the picture or 30 seconds to draw the picture, oh well. It's better than getting a question wrong. Sometimes it's more useful to draw a picture. Okay, you're more likely to get it right. We've got a sphere with a negative charge right here. It experiences a force of 5.60 times 10 to the negative 2 newtons. We know that that force is a force of repulsion. So let's say my producer is over here, my source charge is over here. We know that it's repulsion, so the source charge must be negative to repel it. The field, therefore, must point to the left. points toward the negative producer, and it's opposite to the force. Force was to the right because it was a repulsive force. So this is my producer. This is my experiencer. What do I know more about here, the producer or the experiencer? The water bottle or the earth? The water bottle, the experiencer, right? So let's use that experiencer equation. Let's say E is equal to F over Q. On your data sheet, by the way, this equation doesn't have absolute value signs around it. I prefer to put them around it, but it's not a big deal if you leave it off. F is 5.60 times 10 to the 2 newtons, and Q is, we're dropping the sign of the charge because we always do, 2.1 times 10 to the negative 6. Do the math there. What do we get? 560 divided by 2.1 times 10 to the minus 6. We get 2.67 times 10 to the 8. Well, what would the units be? No. Oh, you know what? I'm glad you said that, though. It's a mistake, but I'm glad you said that. It is so important when you're writing the electric field to put the vector sign over the E, because if you don't, you're going to get it mixed up with what? Energy. This is not energy. This is the electric field. Energy is joules. Electric field is, we're going to say newtons per coulomb, right? Newtons over coulombs. Newtons per coulomb. There's other sets of units that we can use, but for now, we'll go with that one. Regardless of which equation you use, we'll use that one. Yep.
If we had a rating question, or like a rating response question,
yep. The question was, if you didn't hear it, if we had a written response question, and you will down the road, it's quite a ways down the road still, but you had a written response question on a test on electric fields, and you forget to put the arrow over it, as long as you do everything right, no, I wouldn't mark that wrong. But in my experience, you're smart to put the vector sign over top of it, the half arrow over top of it, because it means you're less likely to get it confused with energy and make a mistake because you got them mixed up. Now you said 2 minutes ago, you said the units were going to be joules, right? Because you mixed it up with energy, right? If you put the arrow over it, you might still make that mistake, but you're less likely to make that mistake. So the arrow isn't for my benefit, it's more for your benefit, so that you don't make some other mistake. Okay, yep.
In the question, it says question 6.
Oh. Yeah, you're right, 5.6 times 10 to the negative 2. That's going to affect things. It's 2.67 still, but it should be times 10 to the times 10 to the positive 4. Right? Thank you, Brandon. Does that make sense? Mistake that I made there? Okay, let's have a question or a look on questions 1 and 2 on page 548, please. Okay, here's another one. This time we want to determine the electric field at a position P that's this far from the center of a negative point charge. So here's our negative point charge. It's negative 1.70 times 10 to the negative 6 coulombs. We want to find the field strength over here somewhere, a distance of 2.20 times 10 to the negative 2 meters away from that. What do you got here? Is this your earth or your water bottle? This is your earth, right? This is what's producing the field. What do you have over here? Well, there's not even anything there to experience it, right? It's just a point in space. It's like when I point to that point in space and I say, what's the gravitational field strength right there? There's nothing there experiencing it. What do you know more about? The producer or the non-existent experiencer? The producer. So let's use the producer equation here. We're going to say E is equal to KQ over R squared, 8.99 times 10 to the 9, times the charge of the producer, which is 1.7 times 10 to the negative 6. Drop the sign of the charge, not the sign of the exponent, but the sign of the charge, and divide it by 2.2 times 10 to the negative 2. Just don't forget to square that. Now, some of you look at this and say, I can tell that's a producer. I don't need to draw the picture. But do you see how obvious it is when you draw the picture that we've got a producer here? Hey, take the time. Like, for the amount of time that it takes to draw that out, take the time. It becomes, I think, pretty clear when you do that we've got a producer here, not an experiencer. Let's do the math on this and see what we get. Say 8.99 times 10 to the 9 times 1.7 times 10 to the negative 6. And we'll divide that by, use some brackets here, 2.2 times 10 to the negative 2, and let's square that denominator. 3.16 times 10 to the 7. We'll say newtons per coulomb again, because those are the standard units for the electric field. Now, it doesn't say determine the magnitude, it just determine the electric field. Electric field's a vector. What could we say about the direction of the field there? Can't say right, left, up, down, because I could have drawn it like this, right? What could we say? Yeah, we could say toward the producer. You know it's toward the producer, right? Because the electric field is always toward a negative producer. That's the best that you can do for direction in this question. Draw the picture, figure out what you got, producer, experiencer, and then put down the equation, plug them in. Try these two, please. Okay, one more. Page 550, it says two positively charged spheres, A and B, have charges of 1.5 times 10 to the minus 6 and 2 times 10 to the minus 6, respectively. And they're this far apart. We want to find the field strength midway between the centers of the two spheres. So we want to find the field strength right here at this point P. Hey, at point P, do I have a producer, experiencer, or what? I don't actually have anything at point P, right? It's like saying, here's the Earth right here, here's the sun over there, halfway between the Earth and the sun, what's the gravitational field strength? We don't know what's there, if there is anything there. Is there anything right here at point P? Maybe there is, but if there is, we certainly don't know anything about it. Well, if there's not an experiencer there, then we're certainly not going to use the experiencer equation. These two charges are both producers. They both produce a field at point P. Charge A produces a field this way. Why? Because it's positive and the field goes away from a positive. Now, charge B is also positive. So the field caused by point B at this point right here is going to be to the left, because the field goes away from a positive, toward the negative, away from the positive. If charge B was negative, then field B would point toward the negative, right? But it's not. Both of these fields are away from the respective positives. So what are we going to do at this point? Now that we've drawn this picture and we show which way the fields are pointing, what are we going to do? Let's finish this off and then I'll answer your question, okay? Is this not like those problems we had with 3 charges in a row? You found the force caused by one of them, force caused by the other one, and then you had to add them up? That's exactly what we're going to do here, except it's with fields instead of forces. Field A is going to be KQA over R squared. What would be the value of R? Connor? No.
Well, no, divided by 2.
Divided by 2. Good. So we're going to say R there is 1.65 times 10 to the minus 2. We're going to do the same thing for the green one here, the field caused by B. We're going to say EB is equal to KQB over R squared. And once again, because we're looking for the field strength midway between, R is going to be 1.65 times 10 to the minus 2 again. And then we're going to look for the value of EB. What are we going to do once we find the value of both of those? Yeah, add them up, but of course one of them The green one is going to be a negative value. So yeah, Riley, it's going to have the effect of subtracting them, right? We want to think of it as adding because we're trying to find a net field, and net is the sum. But when you add a negative, it's the same thing as subtract, of course. So we're going to say this one plus negative this one gives me the net field. And if the net field is positive, it's to the right. If the net field is negative, it's to the left. Right? What's the key in this question? As I see it, what's the key? This, right here. Draw that picture right. Okay, you draw that picture wrong, you got no hope of getting the right answer for this. You may be so close, but it doesn't matter. Okay, if it's a multiple choice question, so close is still wrong. Still a 0 to 1. Draw the picture correct, and at least you got a fighting chance. So look at these two questions, please, on page 550. In addition to those two questions, when you're finished those two questions, I'd like you to take a look at worksheet number 8 and do questions 1 to 8 on worksheet number 8. 1 to 8 on worksheet number 8 in addition to these two questions. So it's a total of 10 questions, but we've got almost a half an hour to work on these in class here.